Okay, you made it through part one. Here we go with part two. We're still talking about where all the electrons are according to Schrodinger's model for the atom. They aren't on rings anymore. That was Bohr. He called them orbits. Schrodinger is calling them orbitals, areas where there's a high probability of finding the electron. And we have three different ways for writing where all the electrons are. And they're a little bit annoying, but easier than drawing all of those three-dimensional pictures. So it signifies where all the electrons are according to a pretty complicated mathematical model. So it turns out that Schrodinger's model can still explain why we saw the bright lines. I mean, it certainly should be able to, because we said it was better than Bohr's model. In Bohr's model, the electrons would get excited by heat or light or electricity and jump to a higher energy orbit, and then when they fell back down, give off a photon of light. Well, something very similar happens in Schrodinger's model. He says that when an electron has more energy than normal, which came from if it was exposed to heat or light or electricity, electrons absorb that energy and jump to a higher energy orbital. The only difference really between the two models is that word. And then when the electron falls back down to its ground state orbital, then it gives off energy as a photon of light. Wow, again, that seems almost just like Bohr's model. And it is, except for instead of jumping between orbits, it's jumping between orbitals. When we drew Bohr's model, we could show that the electron was on a ring that was higher up. And again, for Schrodinger's model, it's hard to draw the orbitals. So instead, we use electron configurations to show excited states. If we look at this first one here, it says 1s2, which is how we would start it, and then go across 2s2. That's how we would keep going. 2p6. Yep, that looks normal so far. 3s1. That would get us to sodium, and it followed all the rules. So this is just sodium, and it's a ground state. Okay, let's check out the next one. We've got 1s2, 2s2, 2p6, 3s2. That seems normal so far, gets us to magnesium. Then 3p, 1, 2, 3, 4, 5. And then it skipped one. It skipped this one and went straight to 4s1. Well, that seems like a bad plan. And it violates one of the rules that we have. It violates Aufbau's principle, that you have to fill up lower energy orbitals before you fill up higher ones. So this is considered an excited state. Now, the question is, should it really be potassium, which ends in 4s1, or should it be argon? And it should be argon because it has the right number of electrons to be argon. That is really supposed to end in 3p6. It's just the 3p6 electron jumped into the 4s1 orbital. So if anything is violating the rules for writing electron configurations or doesn't follow our annotated periodic table the way that it's supposed to, then we know it's an excited state. Try the next two and then check your answer. Hopefully you got the same thing as me. The second one is an excited state because it really should just end 1s2. And the last one is a ground state. It looks a little bit like excited state at first, but it really is just a not fully filled last orbital, which is totally okay. That's what silicon's electron configuration is. Another thing we can do with Schrodinger's electron configurations is we can write the electron configurations of ions. They're pretty straightforward, and you should know what ions each of them form from both the periodic table that you have and also from looking at the periodic table Nearpod presentation. So magnesium makes a +2, sodium takes a +1, fluorine takes a -1, and oxygen takes a -2. To figure out the number of electrons they have, you have to think back to our last unit. So magnesium has 12 protons. I know that from its atomic number on the periodic table. That's the number of protons. So if it has a +2 charge, it has to have 10 electrons. Sodium has 11 protons. So if it has a +1 charge, it also has to have 10 electrons. Fluorine has 9 protons, so to have a -1 charge, also 10 electrons. You should be seeing a pattern here. Oxygen has 8 protons, so for a -2 charge, 10 electrons as well. Now let's write their electron configurations. So to get to magnesium, it would be 1s2, 2s2, 2p6, and then to get to magnesium, we'd also have 3s2. But we took away 2 electrons. That's how we get a +2 charge. And if you count these, 2, 3, 4, 10, 11, 12, that's too many electrons. So our +2 charge says we remove 2 electrons, and you always remove the outermost electrons. So these are the electrons that would be removed. So the electron configuration of a +2 charge ion of magnesium would be 1s2, 2s2, 2p6. That's the same electron configuration as neon. It would end right there. So that's the same as neon. For sodium, we would do kind of the same thing. Pause for a second and see if you can do it on your own. Hopefully you noticed that we would remove the last electron from sodium, making it also have the same electron configuration as neon. Fluorine is a negative ion, so it's a little bit different. Its electron configuration would be 1s2, 2s2, 2p5. But because we have an extra electron, what happens is instead of ending in 2p5, it ends in 2p6. Well, that's also the electron configuration of neon. Stop for a second and see if you can figure out what oxygens will be. If you realize that oxygen with a -2 charge is also going to have to end in 2p6 and is also the same as neon, then you're on the right track. This happens a lot. Often elements are going to take charges that will make them isoelectronic with a noble gas. That means that it has the same electron configuration, or the same number of electrons, because everything with the same number of electrons will have the same electron configuration. And it'll be isoelectronic with a noble gas, because noble gases are really, really stable. So because noble gases are very stable, atoms are going to gain or lose electrons to make them like those noble gases and have the same electron configuration as those noble gases. Atoms do this because they're following the octet rule, which you might have also heard about in middle school. The octet rule says that very often atoms will gain or lose electrons to form a noble gas electron configuration. Having 8 electrons in the s and p orbitals is very stable. Notice we ignore the d's. They are not considered the outermost orbitals. And to fill up s and p, you need 2 in the s and 6 in the p. That's 8 electrons. And it's also why it's called the octet rule. Oct meaning 8. So having 8 electrons is very stable. You might have drawn rings for Bohr's orbits in middle school and made sure that you had 8 on the outermost one. This was because your teachers were trying to hammer home this octet rule idea. Again, having 8 electrons in the outermost orbitals, which are s and p, is very, very stable. Those outermost electrons are called valence electrons, and they're the electrons in the outermost s and p orbitals, the ones that are at the end of the electron configuration. And the reason they're so important is because they're the electrons that are most commonly involved in bonding. And bonding is something that's very important in chemistry. It's how atoms get together to make compounds like carbon dioxide or water. So we're going to be very concerned about these valence electrons. You watched the periodic table Nearpod and learned that elements that are in the same column have a lot of similar chemical properties. For example, the alkali metals explode when you put them in water. So elements that are in the same family, one of the reasons that they behave the same way is because they have the same number of valence electrons. The similarities with their valence electrons indicates that they will have similar chemical behavior. At this point, you should be able to answer almost all, if not all, of the questions in your electron configuration practice sheets. Good luck!